Hello. In the previous video I explained that it is possible to establish an edge map using the zero crossing property of the second derivative. So this is what I explained in the previous video. Now the reason why I'm showing this to you again is to not get confused by an important thing. So here, to detect the coordinate of the zero crossing, we do not actually evaluate where a pixel is equal to 0. If we do that, of course, I would get, I can say, replace the pixels where the second derivative is equal to 0 by 1, and this way would get a white color. Now if I do this, I would get, of course, the zero crossing, but I would get other edges, other white colors, other white pixels that are not actually the center of any edge. So I would get white colors in this coordinate and also white color in this coordinate, just because I have a 0 value here and a 0 value here. So we do not detect the zero crossing in this way. I'm going to explain later a simple technique to detect the zero crossing. But for now, I'm going to talk about how to detect, how to calculate the second derivative for a two-dimensional image. Now if you remember, I said in a previous video that the first derivative of a two-dimensional image is calculated using the gradient. And to visualize where the edges are and how sharp they are, we use the gradient magnitude. And the gradient magnitude of an image at a given position is given by this formula. So we square the gx component and the gy component and we add them up. And the gx is just the partial derivative of the image in the x direction, and gy is the partial derivative of the image in the y direction. Now to get the second derivative, what I can do is just to remove the square root of on this formula. So in this way I would have a second derivative that I can write in this way. And this actually is called the second derivative, or the second gradient magnitude is actually called the Laplacian. So this is the Laplacian operator. Now, the thing not to do is to go and use one of the three filters that I already explained, which are Robert, Sobel, and Pruitt, to calculate the gx and gy component, and then square them up and then add them together. So this is not the way we use to calculate the Laplacian in practice. We use rather a special kernel that approximates this formula. So I'm gonna mention two kernels that we can use. So this is the first kernel. I have here 4 minus 1 here, and on the corners I have zeros. This is one kernel and this is another. So instead of 4 I would have 8 and minus 1 everywhere else. Now to calculate the second gradient magnitude of the image, or the Laplacian, all we have to do is to convolve our image with this kernel or with this kernel. Now one important thing to note here is that the sum of the elements of this kernel is 0, and also the sum of the elements of this kernel is 0, and this means that in regions where we don't have an edge, we would get values that are very close to 0. So its response is very weak for constant regions. Whereas if we had an edge, then we would get, as I already explained, two impulses. The first is positive and the second is negative, and we can use that to we can use the zero property, the zero crossing property of that to establish an edge map.